The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Last time we were talking about this valence bond model for describing the bonding, in particular the bonding between atoms in a polyatomic molecule. And we saw that the key to this description was allowing the wave functions, the individual wave functions on an atom to constructively and destructively interfere themselves to form some hybrid wave functions, to form some hybrid orbitals. And then it is those hybrid wave functions that overlap with the wave functions of another atom to form a chemical bond. And in particular, what we treated last time is this Sp2 hybrid wave functions that were centered on carbon, that were centered on nitrogen, that were centered on oxygen. And we saw that these Sp2 wave functions were this linear combination, or this destructive and constructive interference between the S wave function and the three 2p wave functions to form these Sp2 wave functions and correspondingly these Sp2 states. All right? And as I said, we saw that on carbon, we saw that on nitrogen, we saw that on oxygen. And those wave functions end up being pointed to the corner, to the vertex of a tetrahedron, where the atom was at the center of that tetrahedron. So in the case of methane then, if you bond a hydrogen to each one of those Sp2 hybrid wave functions, what you get is a tetrahedral geometry around the carbon. If you had a nitrogen with those Sp2 wave functions around it and you bonded three hydrogens, then you got a trigonal pyramid as the geometry of the ammonia molecule, with those two lone pairs sticking out there at another vertex of a tetrahedron. But remember, we talked about the shape of the molecule as being described by the positions of the atoms and not the positions of the electrons. And we talked about water, Sp2 hybridized. We add two hydrogens to it, we form two bonds, it's planar bent, and then we have two lone pair electrons sticking out of the oxygen. Those are going to play a big role in some of the bonding we're going to look at the end of the lecture today. All right, so we've got to move on, and we got to talk about another kind of hybridization, which we started to talk about last time, which is this Sp2 hybridization. We talked about it on boron, and we saw that the Sp2 wave functions end up being in a plane, which in the case of boron, if we then bonded hydrogens to those Sp2 wave functions, we got a planar molecule for boron H3. But carbon can also undergo this Sp2 hybridization. And so let's take a look at that now. All right, so in the case of carbon, we have to do this electron promotion that we talked about also in the case of the Sp2 hybridization. And then we let now one of the two S wave functions and two of the 2p wave functions hybridize, constructively and destructively interfere. And the result is three Sp2 wave functions, or three Sp2 states with one electron in each one of them. And then one of those p orbitals, or those p wave functions on the carbon, is untouched. That's just the atomic wave function, the atomic orbital on that carbon. And if we look at the picture of all of those wave functions, here it is, right? This is the 2s on the carbon, 2pz, 2px, 2py. And what we did is that we let these three, for example, These three constructively and destructively interfere to form these three sp2 hybrid orbitals, or hybrid wave functions. And the result is that they look like this, right? The result is they all have a large positive lobe on them due to the constructive interference. And they all have a small negative lobe here. And in all of the rest of the pictures that we're going to draw, we're not going to draw that small negative lobe because it just makes it hard to draw. Okay? But the bottom line is that these three lobes lie in a plane. And then, of course, we still have that 2py atomic wave function centered on the carbon, and that is unperturbed. All right, so now what I'm going to do is, since I'm going to put all of these three wave functions on the same plot, right, since they all have the same origin. So that's what I'm doing right there. There it is for the carbon with the three positive lobes of that sp2 wave function all in the same plane. And again, I didn't draw the little part of the negative wave function in this picture. All right, but now what we also have is that 2py wave function, the 2p wave function on the carbon that hasn't hybridized. And, that hasn't hybridized, right? And it's sticking out of the plane of the board, right? That's the 2p orbital that you're used to seeing on the carbon. And it is perpendicular here to the plane in which the sp2 wave functions are sitting. All right. So now what we're going to do is I'm going to take this sp2 hybridized carbon, where the positive lobes of these sp2 wave functions are all 120 degrees away from each other, and where you would say these wave functions had a trigonal planar configuration. I'm going to take this sp2 wave function, and I'm just going to rotate it so that this lobe here is parallel to the floor. I'm going to do that for convenience, as you're going to see why in a moment, and that's what happens here on the next slide. All right, I just rotated this by 90 degrees in particular, so I could put the z-axis here along a bond I'm going to form. All right, so that's the top view. Now, let's look at what this looks like from the side. All right? So from the side, what it would look like is something like that. The carbon is right here at the center. Then the positive lobe, this positive part of the wave function, that's what this is here. This 2py wave function, well, here it is, right? It's perpendicular to this plane that you're looking down on up here. It's perpendicular to this plane. That's that 2py wave function. Positive part of the p wave function, negative part of the p wave function. And then this part of the wave function, well, this is just a projection of these two big positive parts of the wave function, right? This just projects this way and out that way. So that's what it looks like from the side. All right, so now what I'm going to do is I'm going to bring in another sp2 hybridized carbon up here. I'm going to bring it in. It's going to look just like that. And here it comes. And when I do that, what's going to happen right here is that I'm going to allow the 2sp2 wave function from this carbon to overlap with the 2sp2 wave function from this carbon. And I'm going to form a bond. And that's going to be a sigma bond. Sigma because it's going to be cylindrically symmetric around this carbon-carbon bond axis. And it's a sigma bond formed by the carbon 2sp2 hybrid wave function and the other carbon 2sp2 hybrid wave function. All right? So I formed a bond here. And now what I'm going to do is I'm going to bring this C2, or this carbon sp2 hybridized wave function or carbon in again, but I'm going to bring it in, and we're going to watch this view, all right? So we're going to watch it from the side. And this time what I want you to see is what's going to happen here to the 2py wave function, all right? So here it goes. We're going to bring it in, and then this 2sp2 is going to form a bond here between this carbon. But now what happens is that those 2py wave functions, they overlap. They constructively or destructively interfere, all right? If you want to watch it again, right, here it comes in. We're going to make this sigma bond, but now these two lobes are going to interfere, and these two lobes are going to interfere, and this is going to be constructive interference there because they both have positive sign or negative sign, right? And so we're going to have wave function up here and wave function down there, right? We formed another bond right here. The bond that we formed here is going to be called a pi bond. It's pi because it's not cylindrically symmetric around this carbon-carbon axis, right? There's wave function or electron density if you square it up here, and wave function or electron density if you square it down here. But right here along the plane, there's a node in that pi wave function. All right, so this is a pi wave function. It's made out of the atomic wave functions on carbon, the atomic wave functions, the ones that haven't participated in this hybridization. So it's made out of carbon 2py and carbon 2py. All right. So what I've got here, what I got here is a double bond, right? I've got two bonds between the two carbons. I got a sigma bond and I got a pi bond. Hey, that's great. Now, let's bring in some hydrogens. I just did. And when I brought in those hydrogens, well, you can recognize this as ethylene, right? The hydrogens form a sigma bond between the carbon 2sp2 hybrid wave function and the hydrogen 1s wave function. That's what forms the sigma bond. It's sigma because it's symmetric around that carbon-hydrogen bond axis, all right? And the molecule that we have here is ethylene. Now, let's look at that again because this is really very important. Here I show you just those two sp2 hybridized carbons forming that sigma bond. And this just represents here the energy levels as I bring them in. So in this case here, we've got 2 electrons in this sp2 state, and we have 1 electron in each one of the 2py states. And so this represents this sigma bond here, right? And then we made a pi bond, and we'll watch it now from the top, right? We made a pi bond. We let these two 2py wave functions overlap, constructively interfere to form a pi bond, which is the carbon 2py, carbon 2py. All right? So, clue here. Every double bond has 2 bonds. That's why it's double. But every double bond is made up of 1 sigma bond. And the sigma bond is always the overlap between two sp2 hybrid wave functions. And the second bond that always makes up a double bond is a pi bond. The pi bond is always the overlap of 2 atomic wave functions. In the case here of carbon, it's 2p wave functions that have overlapped. All right? That's what a double bond always is. It always is so, whether it's a carbon double bond or a nitrogen double bond or an oxygen double bond. It's always 1 sigma, 1 pi. Okay? All right, and there are the hydrogens. And as we said, those hydrogens there, that carbon-hydrogen bond is this overlap between a carbon 2sp2 wave function and that hydrogen 1s wave function. And now what's the geometry of ethylene? Well, the geometry here of ethylene is that the hydrogen carbon-hydrogen bonds are 120 degrees. Right? That's 120 degrees because that is the result of the hybridization, that 2sp2 hybridization of the wave functions around the carbon. This bond here is 120 degrees, again, because of the 2sp2 hybridization around that carbon. So the geometry of this molecule is planar. Right? All of these atoms are in a plane. Those 6 atoms are in a plane. And the bond angles here are all 120 degrees. Okay, now, if you see a carbon that's got a double bond, if you see a nitrogen that's got a double bond, if you see an oxygen that's got a double bond, hey, that is always a clue that that carbon, that nitrogen, that oxygen has a hybridization of 2sp2. All right? Double bonds have this hybridization always. Okay? So if you're asked to tell what the hybridization is around some atom, if it's got a double bond to it, it's a 2sp2 hybrid. Okay? Okay. Now, what I want to do is I want to take this 2sp2 hybrid and build a larger molecule. All right? So I'm going to take this carbon 2. I'm going to take the 2 carbons here that are bonded via this 2sp2 hydrogen. So here's 2 of them. And here's another 2, and they're kind of strategically placed for what it is I want to do. And of course, this is the sigma bond between the 2 carbons. Right? Carbon 2sp2. Here's the carbon 2sp2 sigma bond. Okay? All right, now what I'm going to do is that I'm going to bring in another carbon that is sp2 hybridized. All right? Here it comes. And again, it's strategically oriented so that right here, I have now formed another carbon bond, another sigma bond between the carbon 2sp2 wave function and the other carbon 2sp2 wave function. And same thing right here. Okay? I just formed 2 other sigma bonds. And now I'm going to bring in a 6th carbon, sp2 hybridized. And it's going to come in from this side. And again, it's strategically oriented. So I've just formed here, right, another sigma bond between these 2 carbons and another sigma bond between these 2 carbons. Hey, look at this. It's beginning to look a lot like benzene. Okay. That's my favorite part. Here come the hydrogens. Hey, this is going to be benzene. All right, so what did I do here? I made some sigma bonds. I made 6 sigma bonds, right, between the carbon 2sp2 wave functions and the hydrogen 1s wave functions. Okay? So now I got all of my atoms there and almost all of my bonds. However, we've got to do something here about these 2 p atomic wave functions that are centered on the carbon. All right? We're not done yet. All right, so what's going to happen to them? Well, they're going to overlap, constructively and destructively interfere. And to see that, let's take this benzene molecule and rotate it 90 degrees so that we're going to look at it from the side-on view instead of the top view. So there it is. All right, here are my carbon-carbon sigma bonds, the 2sp2, 2sp2 bonds. Here's my sigma bond between the hydrogen and the carbon 2sp2 wave function. And now I'm going to let the 2p, the atomic wave functions, not the hybrid wave functions, the atomic wave functions on the carbon, I'm going to let them constructively and destructively interfere. Okay, and here goes. Well, they're going to overlap, and ta-da, I got something that looks like a pi bond here, right? I've got wave function above the plane of these atoms, and I got wave function below the plane of these atoms. It is a pi bond that is formed by the overlap of the 2p wave functions, the atomic wave functions on carbon. All right, it's pi because it's not symmetric around the the bond axis, right? There's density up here, density up there, but not in the plane. Okay, so let's look at it again from the top view. All right, so what did I do? Well, I let these 2p wave functions here overlap. So let's look at that a little more carefully. What exactly did I do here? Well, what I did is, for example, I let the 2p wave functions on these two carbons overlap to form a pi bond. I let the 2p wave functions on these two carbons overlap to form a pi bond. And I let these two 2p wave functions overlap to form a pi bond. Well, that's very nice, but hey, I could also have let the 2p wave functions on these two carbons overlap, or these two carbons, right? In other words, I could have made a pi bond between these two carbons, or these two carbons, whoops, or these two carbons, right? So which one do I choose? Well, in recitation the other day, you should have looked at the Lewis structure of molecular benzene or benzene. And what you should have seen is that you would be able to write several different Lewis structures, all which have the same set of formal charges, and that you wouldn't be able to decide which structure you should have based on the formal charges. That rather what you had is a resonance structure, and that is exactly what you have. Instead of these 6 extra electrons, which are centered on the carbon, those 2p electrons, right? There's one here, one there, one there, one there, one there, one there. Instead of those two, each one of those electrons being shared between just one of the adjacent carbons, those 6 extra electrons are actually delocalized around all of the carbons. And so what you're going to form here is not a clear double bond between this carbon and this one and this one. Instead, what you're going to form is a kind of a half of a pi bond, right? That is, you're going to let those 6 electrons be equally distributed, so to speak, around all of the 6 carbons. And so this pi bond here isn't quite a full pi bond. It's kind of a half of a pi bond, all right? Because this carbon is sharing its 2p electron with this carbon and with this carbon, and vice versa, right? All the way around. And so we have this resonance structure. I drew this as kind of a fuzzy green line there. We have these 6 pi electrons that are delocalized amongst these 6 atoms of this carbon ring. Okay? So these double bonds here are really a bond and a half, right? They are, these bonds, this bond is more than a single bond in terms of its bond strength and in terms of its distance. It's closer than a single bond, but it isn't as strong as a double bond, nor is it as short as a double bond. It's somewhere in between. All right? That's the structure here of benzene. Okay? Okay. So that takes care of Sp2 hybridization. Now, we've got one other kind of motif, and that's called Sp hybridization. And we're going to use carbon again as the example of this Sp hybridization. And again, since we're starting with carbon here, we're going to have to undergo this electron promotion process. We're going to take an S electron. Are there some questions here that I can help you with? No, huh? Okay. We're going to take that S electron and promote it to the 2p state. And then we're going to do a hybridization. But this time what we're going to do is we're going to let the 2s atomic wave function hybridize with one of the 2p wave functions. Okay? And the result then is that we're going to have a new wave function that we're going to call Sp. And there's only going to be 2 of them because we only let one of the 2s and one of the 2p's constructively or destructively interfere. So we're going to get 2 Sp states or 2 new Sp wave functions. Each one has got an electron in it. Each state's got an electron in it. And then we've got left over 2 atomic states centered on the carbon, the py and the px. Each one has an electron in it. Okay? Yes?
Does it matter which 2p state you choose to hybridize?
Well, by convention here, yes. The p state we're going to hybridize is going to be 2pz. Okay? And that's because that is the bond that I am going to make another, that is the wave function I'm going to make a bond to. And I want that along the internuclear axis. But in real life, you can't tell what's x, y, or z. Okay? But by convention, we're always going to put the z axis, right, along the bond axis. Okay? And I might say something, I'll say a little more about labeling py and pz in an example that I'm going to do in a few minutes. All right? So I hope that will clear things up. Okay, so in the picture form, here's our 3 atomic wave functions again. And I'm going to let these 2 constructively, destructively interfere. And the result is then 2 new Sp wave functions. Now, given that I'm letting only 2 wave functions constructively and destructively interfere, it's a little bit easier to see how I get these shapes. All right, so here goes. This 2s wave function, remember the 2s wave function never always has one sign. Say it has a plus sign. It never crosses the axis. There are no nodes, right? No radial nodes. When you have a node, that's when the wave function changes sign. Okay? So I'm going to put that 2s wave function in the same place in space as this 2pz wave function. When I do that, since this is a wave, it's going to constructively, destructively interfere. So up here, where I'm constructively interfering this positive wave function with the positive part of the 2pz wave function, hey, I'm going to get a lot of positive wave function. That's what this lobe, that's where this lobe comes from. But down here, where this is positive and this is negative, well, that's going to be destructive interference. And because this negative part of the 2pz lobe is actually larger than then the 2s is positive, well, I'm going to have a little bit of leftover of a negative wave function. All right, so here it's easier to see how you get this shape by the interference of that wave function with that wave function. And then correspondingly, I'm going to let this wave function and that wave function destructively interfere. So if this is still positive, positive minus a positive is going to give me a little bit of a wave function, and it's going to be negative. And then positive minus a negative, that's going to give me a positive. Here's my big positive wave, part of the wave function. All right, that's a little bit easier to see now than in the Sp3 case where it's not so easy to see. Okay? All right, so these are now my two new 2p wave functions. And the atomic wave functions here haven't done anything to them. Okay. So now I'm going to put these wave functions all on one plot. Hey, they all have the same origin. It's the carbon right in the center. So I'm going to put them all on one plot. Here they are. And what I did is that I rotated the z-axis was going up and down here. The z-axis in this picture is coming this way. It's parallel to the floor. Again, strategically placed for the next bond formation. Okay? All right, but here you can see the 2px wave function, the atomic wave function, untouched. And perpendicular to it, you can see the 2py wave function, untouched. Okay? Okay, so now I'm going to take another sp carbon wave function and bring it in. And I'm going to let the sp wave functions on the two carbons overlap so that I form a sigma bond. Sigma formed by the carbon 2sp, carbon 2sp. Hey, that's my sigma bond there. Okay. But now you know what's going to happen. We're going to let the atomic wave functions on the two carbons constructively, destructively interfere. Oh, I'm going to bring in hydrogens first. Sorry. We brought in the hydrogen and formed this carbon, this sigma bond between the carbon 2sp wave function and the hydrogen 1s wave function. And we've got acetylene. Except now we've got to let the 2p atomic wave functions interfere. The atomic wave functions on each carbon interfere. Except I wanted to point out this geometry. I got this all wrong. Okay, this is 180 degrees, right? Because the sp wave functions lie in a line. So the hydrogen, carbon, carbon, hydrogen here, right? That bond angle is 180 degrees. We have a linear molecule. Okay, and now we're going to let the 2p wave functions interfere. When we did that, we're going to form a pi bond, right? The interference of this 2py and this 2py. This is going to be a pi bond. It's pi because it's not cylindrically symmetric around this carbon-carbon bond axis. There's electron density above the plane of the slide and below the plane of the slide. So we've got a pi bond here. And then finally, we're going to let these two atomic wave functions constructively and destructively interfere. Right? The 2px. Again, we're going to form a pi bond. It's pi because it's not cylindrically symmetric around the bond axis. There's electron density up here and electron density up there. Hey, what we've got here is a triple bond. We have between the two carbons one sigma bond, one pi bond, and another pi bond. The two pi bonds are perpendicular to each other. That's important. So a triple bond is always composed of one sigma bond and two pi bonds. That's the case whether you're looking at a triple bond on carbon or nitrogen or anything else that forms a, well, almost anything else that forms a triple bond. Okay, but for your intensive purposes, carbon, nitrogen, going to form a triple bond. Okay? Okay, so that's important here. Okay. So those are our hybridization schemes that we're going to look at, and it's going to allow us to describe the bonding in lots and lots of molecules. And one of the molecules that I want to describe the bonding of is this molecule. It's methyl nitrate. Okay? And this is going to help you out on the homework here. All right, so suppose you're asked to describe the bonding in methyl nitrate, and you're given this structure. Well, you know, the first thing you have to do is to write down a skeletal structure. And to actually, in your mind, get down what the Lewis structure is for methyl nitrate. All right? So a couple of days ago, I told you that when you see a CH3 species like that, that's a methyl group. Hey, that's always terminal. That's a carbon with 3 hydrogens bound to it. And so that's what we're going to do. We're going to make this carbon there with the 3 hydrogens bound to it. And then if you've got a long molecule like this, one place to start is to then just bind this atom to the next atom. So I did that. I put the carbon bound to the oxygen. And then following that rule, I took the oxygen, bound it to the nitrogen. And then following that rule, I got 2 oxygens here. I put the oxygen on this nitrogen and the oxygen on that oxygen. Okay? And then I drew the Lewis structure. I counted my electrons, drew it up. There it is. Or there's a Lewis structure. But now what I'm going to do is I'm going to calculate the formal charge. So all of these atoms here, if I do it right, have a 0 formal charge. I then find a formal charge of +1 on the oxygen and -1 on the nitrogen. And I see that the sum of the formal charges is 0, and the overall charge on that molecule is 0. So it looks like I did everything right. However, is this the correct Lewis structure for methyl nitrate? No, it is not the correct structure for methyl nitrate. And it isn't, because we've got a negative formal charge on the nitrogen and a positive on the oxygen, and oxygen is more electronegative than nitrogen. So this is not an adequate structure for methyl nitrate. This does not describe the chemical bonding in methyl nitrate. So what does? Well, to do that, let's look at the board here. Whoops. I was going to raise the screen. Okay, so let's look at the bonding here in methyl nitrate. So here's another Lewis structure that I could draw. All right, CH3, oxygen. And then I could have put the double bond here between the oxygen and the nitrogen. And then I could have bonded the 2 oxygens to that nitrogen. And there's a bunch of lone pairs here, right, on the oxygen. That's all okay. But now, if I go and calculate the formal charges on that, well, I'm going to get a +1 on this oxygen, right? I'm going to get a +1 on that nitrogen. I'm going to get a -1 on this oxygen and -1 on that oxygen. Hey, that's a lot of distribution of charge here away from the distribution of charge in the isolated atom. So let's see if we can do a little better. So again, starting with the methyl group here at the end, let's do this. Let us bond the oxygen to the carbon, and then singly bond that nitrogen to the oxygen, and then doubly bond one oxygen, and then singly bond the other oxygen. And there's going to be a resonance structure to this, right? because I could have switched where the double bonds were here. And if I go and I calculate the formal charges, I find now everything's got a 0 except the nitrogen has a +1 and this oxygen has a -1, and that's a much better situation than a lower energy situation than a +1 on an oxygen and a -1 on the nitrogen. All right, so there's the resonance structure. I won't draw it, but that is the Lewis structure here for methyl nitrate. Now, clue. If you see an NO2 like that, written like that, hey, that is always going to mean the two oxygens are bound to the nitrogen. And if you ever see the word nitrate, like in that expression, that means all of those oxygens are going to be bound to the nitrogen in some way. Okay? So on an exam, if you see an NO2, those two oxygens are going to be bound to the nitrogen. If you see the word nitrate, the 3 oxygens are going to be bound to the nitrogen. Yes?
Why don't we form another double bond between the nitrogen and the oxygen?
If I do that, then I'm going to have these 5 bonds to the nitrogen. Okay? And that is going to give you a very high formal charge. It's not going to be the lowest energy structure. Okay? Okay, so that's our structure. But now the question is to describe the bonding in this molecule. So let's do that. Let's describe that bonding. And let me erase this structure here. Do that. Okay. So what do we have? We have 3 carbon-hydrogen bonds. And this carbon here is bonded to 4 different atoms. That carbon has no double bond, has no triple bond. If it's bound to 4 different atoms and it has just single bonds, the carbon is always Sp2 hybridized. All right, that's something to know. So what that means is that these carbon-hydrogen bonds are sigma bonds. They're sigma bonds formed between the carbon and the S2sp3 wave function and the hydrogen 1s wave function. All right, that describes the bonding in the carbon-hydrogen bonds. Okay, what about this bond, the carbon-oxygen bond here? How do we describe it? Well, we already said this carbon is Sp2 hybridized. And so we can write this carbon as Sp3. And then this oxygen here, well, this oxygen has got 2 bonds to it. It has no double bonds, no triple bonds, so this oxygen is also Sp2 hybridized. This oxygen looks like the oxygen in water. Right? So this is going to be a sigma bond. It's going to be symmetric around that axis between carbon 2sp3 and oxygen 2sp3. Hey, we got that bond. Okay, next we have an oxygen-nitrogen bond. How do we describe the oxygen-nitrogen bond? Well, the oxygen, we already said, was 2sp3 hybridized. So we know that. But this nitrogen's got a double bond to it. If it's got a double bond to it, well, that nitrogen is 2sp2 hybridized. But this is still a single bond between the oxygen and the nitrogen there. It's symmetric. And so that bond is a sigma between the nitrogen 2sp2 wave function and the oxygen 2sp3. Okay, next, the nitrogen-oxygen double bond. How are we going to describe that? Well, it's a double bond. It means we got 2 bonds. One of those bonds is a sigma bond, as I said. It's going to be a sigma bond between the nitrogen 2sp2 wave function and the oxygen 2sp2 wave function, because, hey, oxygen here is also double bonded. If we use that rule, we'll consider the oxygen to be 2sp2. It's a sigma bond. But now we got two bonds, so the second one has to be a double bond. What's that double bond going to be? Well, it's going to be between the nitrogen 2p wave function, because the pi bonds are always between the unhybridized wave functions. And notice I'm going to leave out the x or the y here, because I don't really know. Okay? And between the oxygen 2p wave function. I left out the x and the y there. All right? And then finally, I have the nitrogen-oxygen bond, that second nitrogen-oxygen bond. And what do I have there? Well, it's a single bond. It's going to be sigma. It's symmetric around the axis. It's going to be between the nitrogen 2sp2 wave function and the oxygen 2pz wave function. Okay? It's going to be 2pz in that case because we're here along the bond axis. Okay? It's a sigma bond. It's not a pi bond. The sigma bonds are along the bond axis. Okay? All right, so that's methyl nitrate. Now, I'm a little bit rushing to do something here, and that is I want to describe to you one other kind of bonding, but this is a bonding that is not a bonding within the molecule, but it's, I'm going to do this. It's actually bonding between molecules, and this is called hydrogen bonding. All right, in hydrogen bonding, what you have to have is a hydrogen. And you have to have a hydrogen bonded to an electronegative element like oxygen. So a good example is water, right? Water is bound to an electronegative element. We got two lone pairs. But in hydrogen bonding, you've got bonds between molecules. This is intermolecular bonding. And what happens is that this hydrogen here will interact very strongly with the lone pair electrons here on its neighboring oxygen, forming a bond. It does so because this hydrogen is kind of de-shielded. The oxygen, being so electronegative, has kind of pulled all the charge toward it. So this hydrogen kind of looks like a little bit positively charged, delta plus, where this is kind of delta minus. And so this hydrogen being really small, hey, it can get close to the oxygen lone pairs where there's a lot of electron density and form a bond. And that bond ranges from 20 to 60 kilojoules per mole. Certainly not as strong as a covalent bond. You know, CH bond, it's 400 kilojoules per mole, but about the 10th of that strength. And it turns out to be very important. Hydrogen bonds determine the properties of water. They determine the structure of proteins. DNA owes its helical structure to hydrogen bonding. Trees stand up straight because of hydrogen bonding in the cellulose chains. The strength of nylon is determined by hydrogen bonding, and whether or not you have a bad hair day is determined by hydrogen bonding. For example, on the slides on the side, what you see is the protein of hair. This is a polypeptide. It's a repeating unit here of CO, CH, NH. CO, CH, NH, again and again and again. And here's another repeating, here's another polypeptide or another peptide strain with this repeating unit. Well, what happens Well, what happens when your hair is actually wet, what happens is that the hydrogens on the nitrogen, you can see in that chain up there, what happens is that they are hydrogen bonded to water molecules. And you can also see in the second chain over that the oxygen on the carbon here is hydrogen bonded to a water molecule. So when your hair is wet, the actual polymers in your hair kind of slip by each other, right? However, if you then take your hair and you put it in some very strange configuration and you dry it, right? You remove these water molecules that are hydrogen bonded to your hair. Well, what happens then is that these two chains now kind of lock into registry. They kind of bond together because these water molecules are gone here. And so now they hydrogen bond to each other. The hydrogen bonds to the oxygen on the CO, and the two chains are in registry. And then when you let your form go, well, then your strands actually stay in that registry for a little bit until the humidity wipes that out. Okay? Bad hair day. See you on Friday.